Imagine standing on a planet that looks just like Earth. It has blue skies, green forests, and liquid water. But the moment you try to walk, your legs just buckle. Every single step feels like you're carrying a backpack full of rocks. You weigh 3 times what you normally do. Jumping, that's almost impossible. And running leaves you gasping for air within seconds. Welcome to a super Earth. A rocky planet, larger and more massive than our own. And guess what? They are the most common type of planet in our entire galaxy. But as you'll soon see, bigger is definitely not better. Super Earths are defined as rocky planets with a mass somewhere between 1.5 and 10 times that of Earth. They're larger than our world, but smaller than Neptune. So, not gas giants, not ice giants. They are rocky worlds with solid surfaces, and potentially, even atmospheres and oceans. For the longest time, astronomers thought planets like these would be incredibly rare. We assumed most planets would either be small and rocky like Earth and Mars, or massive and gaseous like Jupiter and Saturn. But when we finally started finding exoplanets, we discovered something truly surprising. Super Earths are everywhere. Roughly 30 to 50% of all Sun-like stars have at least one super Earth in their orbit. They outnumber Earth-sized planets. They outnumber gas giants. They are the galaxy's default setting for a planet, but our solar system doesn't have one. We have our small rocky planets and our large gas giants, but no super Earths. We are the exception to the rule, and that raises a deeply troubling question. If super Earths are so common, so standard, why don't we have one? Was it just luck? Or is there something about these massive worlds that makes them fundamentally hostile to life as we know it? Let's start with the most obvious difference: gravity. The gravity on a super Earth would be absolutely crushing. Here on Earth, gravity pulls you down with a force of 1 g on a super Earth with, say, twice the mass and a slightly larger radius. The gravity could easily be 2 or even 3 Gs. What does that actually mean for you? Well, if you weigh 70 kilograms on Earth, you'd feel like you weigh 140 or even 210 kilograms on a super Earth. Everything becomes an immense struggle: walking, running, even just standing up. Your bones would need to be far thicker and denser. Your muscles would have to be incredibly powerful. Your heart would have to work constantly, much harder than it does here, just to pump blood upward against that relentless pull of gravity. Evolution on such a world would favor short, stocky, heavily built organisms. You wouldn't find any tall, slender creatures, and you can forget about birds. Flight would be nearly impossible. The sheer amount of energy required to lift off the ground would be enormous. And what if intelligent life did evolve on a world like this? Forget about space travel. On Earth, we can launch rockets into space with chemical fuel. It's hard, but we can do it. On a super Earth with 3 times our gravity, that same rocket would need to be exponentially larger to achieve escape velocity. Maybe 10 times the size, or it would need some kind of advanced propulsion we can only dream of. Nuclear engines, antimatter, something far beyond our current technology. A civilization on a super Earth might look up at the stars and come to a horrifying realization: they re-trapped, forever bound to their world by the crushing weight of their own planet. Now, let's talk about the atmosphere. Because of their stronger gravity, super Earths can hold on to much thicker atmospheres. Much thicker. On Earth, our atmosphere thins out pretty quickly as you go higher. At just 10 kilometers up, there's barely any air. On a super Earth, the atmosphere could be hundreds of kilometers thick and dense, so dense that the surface pressure could be 10 or even 50 times higher than what we experience on Earth. This creates a runaway greenhouse effect. Heat from the planet's star gets trapped by the thick blanket of gas. The surface temperature rises and rises. If the atmosphere is too thick, the planet becomes a literal pressure cooker. Water boils away into steam. The surface becomes a scorching, toxic wasteland where life simply cannot survive. This is basically what happened to Venus, and Venus is only slightly smaller than Earth. Imagine a super Earth with even more gravity and an even thicker atmosphere. It could easily become a runaway greenhouse world. Hot, toxic, and completely lifeless, but not all super Earths are doomed. Some might exist in the habitable zone of their star, that sweet spot where it's not too hot and not too cold. With the right balance of atmosphere and distance from its star, liquid water could exist on the surface. And where there's water, there might be life. One fascinating example is a planet called Kepler-2b. It's a super Earth about 2.5 times the size of our own planet, orbiting a sun-like star right in the middle of its habitable zone. We don't know for sure if it has a solid surface. It could be an ocean world, covered entirely in water. Or it might have such a thick atmosphere that there's no real surface at all. But it is possible, just possible, that life exists there. Another candidate is K218b. This is a massive super Earth, about 8 times the mass of our planet. Recent observations have suggested it has water vapor in its atmosphere. It might even have liquid water oceans hidden beneath clouds of hydrogen and helium. But here's the catch. The atmospheric pressure on K218b might be so incredibly high that any ocean would be more like a layer of compressed steam. Not quite liquid, not quite gas, but a strange state called a supercritical fluid. Could life exist in such a bizarre environment? Maybe, but it would be nothing like the life we know on Earth. Let's move on to geology. Here on Earth, we have tectonic plates that shift slowly over millions of years. Continents move, mountains rise, and earthquakes happen. But for the most part, the process is gradual. On a super Earth, tectonic activity could be absolutely extreme. The higher gravity means more pressure on the planet's mantle. This generates more heat and more convection. The crust might be thicker and harder to break, or it might fracture more violently and frequently. Earthquakes on a super Earth could be truly catastrophic, potentially reaching magnitude 10 or even higher on the Richter scale. Entire regions of the crust could sink into the mantle. Volcanic eruptions could be so powerful that they blacken the skies for years at a time, blocking out the sun. Any life on such a world would need to adapt to constant geological chaos, or it would simply be wiped out over and over again, never getting the chance to evolve beyond simple microbial organisms. And then there's the magnetic field. Earth has a strong magnetic field generated by its molten iron core. This invisible shield protects us from harmful solar radiation. Without it, the sun's particles would strip away our atmosphere and sterilize the surface. A super Earth, with its larger core, might have an even stronger magnetic field, which sounds good. But it could also lead to violent magnetic storms. Fluctuations in the field could cause auroras visible even at the equator, but also radiation spikes that would fry any electronics and could disrupt biological processes. Life on a super Earth would need to be incredibly resilient, tough, and adaptable, built to survive one extreme after another. But here is perhaps the darkest possibility of all. What if super Earths are so common because they are evolutionary dead ends? What if life can start on these worlds, but it can never truly advance? Trapped by gravity, crushed by the atmosphere, shaken apart by tectonics, never able to develop complex technology, never able to leave its home world, never able to send a signal out to the stars. We search for intelligent life in the universe. We listen for radio signals. We look for signs of advanced technology. But what if most of the intelligent life in the galaxy is stuck on super-Earths, looking up at the same stars we do, but knowing they can never, ever reach them? In the end, super-Earths remind us of a fundamental truth: size matters. Earth isn't special because it's the biggest or the most massive. It's special because it's just the right size. Small enough for life to one day escape its gravity, large enough to hold onto a protective atmosphere, and stable enough for evolution to take its slow, patient course over billions of years. Super-Earths might be beautiful, potentially habitable worlds, but they might also be prisons. And that should make us incredibly grateful that we live on a world that eventually let us leave. Thank you for joining me on this journey. If you enjoyed exploring the cosmos with us, don't forget to like, subscribe, and hit that notification bell for more deep dives into the universe's greatest mysteries. Until next time, keep looking up.